Okay. Hello, discrete math students. Okay, so I don't want this video getting extremely long, so let's just work on Mathematica for this lecture or this lecture video. I'm still interested in working on some of those prime number problems in chapter 4. Hold on one sec. Okay, let's look at a few of those prime number problems in chapter 4, okay? Here we go. Okay, so number 66. Identify the correct steps involved in proving that a to the power m plus 1 is composite if a and m are integers greater than 1 and m is odd. Check all that apply. So basically, it's giving us two choices. A to the power m plus 1 is a plus 1. Excuse me. A to the power m plus 1 is equal to a plus 1 times a to the power m minus 1 minus a to the power m minus 2 plus a to the power m minus 3 minus a to the power m minus 4 all the way until we get to a to the power 0, which is 1. Or is it a minus 1 times the same thing? Well, actually, it's not exactly the same thing. This is a minus 1 over here, and this is a plus 1. I believe this is the answer, but why don't we just check? Why don't we check to make sure, okay? So let's do an example. How about a to the power 5 plus 1? A to the power 5 plus 1. I believe that's going to be a plus 1 times a to the power 4 minus a to the power 3 plus a to the power 2. Sorry, guys, I have a sore throat this evening. A to the power 2 minus a plus 1. Okay, let's do a little high school algebra, okay? So we can do a to the power 4 minus a to the power 3 plus a to the power 2 minus a plus 1 multiplied by a plus 1. Okay. So then we're going to have, and you know what, let's change colors. Or maybe we can do that one. Okay. So of course, guys, if we multiply by 1, that doesn't change anything. So we're just going to have a to the 4th minus a to the 3rd plus a squared minus a plus 1. Okay. Now we have to multiply by a. So that's going to be, hey Chachki, I'm just talking to my dog, guys. Hey Chachki, a to the 5th. That's going to be minus a to the 4th. That's going to be plus a to the 3rd. That's going to be minus a squared. And that's going to be, 1 second. Wait a moment. But you know what? If this turns negative a times plus 1 is going to end up being negative a. Oh, I'm sorry. I'm multiplying by 1. Why am I multiplying by 1? I'm multiplying by a. So negative a, yeah, we already did that. So negative a times a, no, we did that. That's going to be negative a squared. And then, of course, 1 times a. Sorry about that. Had a senile moment there. Okay. Let's change colors. So then we're going to have a to the 5th. These terms cancel. These terms cancel. These terms cancel. These terms cancel. Plus 1. So a to the power 5 plus 1 is equal to a plus 1 times a to the power 4 minus a to the power 3 plus a to the power 2 minus a plus 1. So this is the same thing as saying m is equal to 5. This is, m minus 1. This is m minus 2. This is m minus 3. This is m minus 4. And of course, this is a to the power 0, which is really the same thing as 1. Okay? So it looks like this is the answer. As both a and m, as both a and m are greater than 1, we have 1 is less than a plus 1, which is less than a to the power plus 1, because a and m are greater than 1. So then a to the power plus 1 is going to be greater than 1, and a plus 1 is in between. Thus, we can see that a plus 1 is a proper factor of a to the power m plus 1. Thus, we can express a to the power m plus 1 as a product of two proper factors, which means a to the power m plus 1 is composite. Composite means the same thing as not prime, right? So there are two types of integers. There are prime integers and there are composite integers. 2 is prime, 3 is prime, 4 is not prime because 4 is equal to 2 times 2. 5 is prime, 6 is not prime because 6 is equal to 2 times 3, okay? Easy enough, right? I should be able to check my answer. Okay, let me submit this. You have 111 incomplete questions. Yes, I know. So everything else will be marked wrong, but 66 should be correct. Okay, so everything should be wrong except 66, because that's the problem I just worked on. And 66 is correct. Looks good. Okay, so let's do a few more problems that involve prime factors. Prime factors. All right, let me take some soda. It's been a long day, guys, and I'm very tired, and I have a sore throat. Sorry about that. All right, let's do some of the prime factorization problems using Mathematica, and that's going to be all for tonight's lecture. No. here we go. Okay, let's look at problem number 65. Identify the prime factorization of 10 factorial. First of all, what is 10 factorial? 10 factorial is equal to 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. That's a pretty big number. Okay, that's the definition of 10 factorial. 0 factorial is equal to 1. That's the definition of 0 factorial. And 1 factorial is also equal to 1. Let's see if we can use Mathematica to help this. Let's see if we can use Mathematica to help us solve this problem. Okay, so basically, there are several things we can do. Let's say that I want a list of prime integers from 2 to 100. 2 is the smallest prime integer. What I could do is this. Cases, range 2 to 100, num, prime q num. This is going to give me all the prime numbers or all the prime integers from 2 to 100. So this is basically a filter. Cases is a type of filter. Cases is a type of filter. Let's do another example. Let me see. Okay, so the very first letter of my name is D. So let's see. Greek gods would be, Zeus, Hera, Aphrodite, Athena, Ares, Poseidon, Hades, Hecate, Demeter, Persephone, Hephaestus, Hestia, Heracles, Hermes, Apollo, Artemis. I'm sure I'm forgetting someone. Sorry. Okay. Cases, Greek gods. What should I call my variable? God. And I want the first letter of God to be equal to H. Oh my. That didn't work. Oh, no wonder. String park. String park. Okay. Okay, so I'm getting back the names of the gods I'm getting back only the names of the gods whose first letter, that's really bad English. I am getting back the gods, the list of gods whose names begin with the letter H. Everything else has been filtered out. Everything else has been filtered out, okay? I believe I can use select to do pretty much the same thing, but the select has a different different syntax. So string part, the hash is a placeholder. That's all it is. It's a placeholder equal to h. And whenever you create a placeholder for an anonymous function, you have to end with the ampersand. I'm recording a lecture now, so don't turn on the TV sound until I'm done, okay? Okay?
What?
No TV sound.
I know.
I'm recording a lecture. Okay, thank you. Okay, so that should be okay. Greek gods.
You don't even have to tell me.
Okay, just checking. All right, so why? Okay, hold on. String or list of string? Interesting. Hold on one second. String part 1 is equal to h. Okay, same thing. Except here, I have to create a lambda function or an anonymous function. And you do that using the hash symbol, and you must conclude with the ampersand. So it's a little bit different, just slightly different. Slightly different. Okay? Okay. So how are we going to solve this problem? I'm going to create a function, and I'm going to call it prime factors helper. And we're going to start with an empty list. Well, this will be, factors will be an empty list. And then we're going to start with primes is going to be another list. And then my number, that'll be another list. All right. Oh, I'm sorry, number is not a list. This is a number. So for example, when I initially call this function, factors will be empty. It's going to be an empty list, and I'm going to start filling it up with factors. This will be a list of prime numbers that could be factors of the number, and this will be some number that has to be greater than or equal to 2. Yeah, sorry, did I say list before? It's not a list. It is not a list. It is a number. Okay. Let's see, how should we do this? The algorithm is finished when primes is empty or number is 0. So if the length of primes is equal to 0, or I can also type it this way, escape or escape, either way. I can type it like this, or I can make it look fancy, escape, double pipe, escape, or number is less than or equal to 0, because I'm going to keep using because I'm going to keep using integer division, and integer division will eventually reduce this number to 0, or I'm going to use up all the possible prime numbers, okay? So then simply give me back the list of factors. So if I've used up all the numbers in my primes list, or my number is less than or equal to 0, give me back the factors. Okay. Otherwise, consider the possibility if number mod, oh, actually, before we even do that, okay. So before we even do that, we have to dissect our list. We have to take the list apart. So P, I'll call it P short for prime number. You could call it prime number if you want to. Prime is equal to primes 1. That's going to be the first number in the list. Semicolon, because I'm chaining a bunch of commands together, okay? Other primes will be the rest of my list. Okay, remember that in Mathematica, the first index is 1, not 0, right? Semicolon. You need that semicolon because otherwise this is not going to work. Because remember, this whole thing is actually an else statement. So you need those semicolons in order to join them together into one else statement. If you separate them with commas, Mathematica will not understand what you're trying to do. All right? So then if number mod prime is equal to 0. Remember, prime is right over here. Then prime factors helper. So prime is a factor of the number. Factors join prime. We're still going to use the entire primes list because even if a number, like for example, 2 is a factor of 16, all right? 2 goes into 16, right? Because 16 is 2 times 8. But you can't throw away the 2 because 2 is also a factor of 8. You can't throw away the 2 because 2 could be a factor of the next integer. So you can't throw that number away. You may need it. You may need it. Okay, so primes and the number integer division, number divided by prime. Okay, or else prime factors helper, we're not going to add the prime number to factors. We're going to discard the first prime number and just stick with, everything else in the primes list except the first number, which is going to be other primes. And since prime is not a factor of the number, we're not going to divide by the prime. We're just going to have number. Okay, shift enter. Let's see if this works. Prime factors helper. 2, 3, 5, 7, 10. Sure, 2 times 5 is equal to 10. Prime factors helper. 2, 3, 5, 7, 11, 13, 17, 19, 23. Let's see if that's true. 2 times 2 times 2 times 5 times 5 times 5 should be 1,000. Or I could type 2 times 2 times 2 times 5 times 5 times 5. Is it really equal to 1,000? Yes. So the function works really well. However, there's still a question here. How many primes are we supposed to use? Do we use 2, 3, 5, 7? Do we use 2, 3, 5, 7, 11? Do we use 2, 3, 5, 7, 11, 13? I mean, how many prime numbers are we supposed to look at? So the thing to remember is this. If 2 is a factor of the number, if 2, which is the first prime, the smallest prime, if it's a factor of the number, then you're going to have 2 multiplied by 500 is equal to 1,000, which means, in my opinion, it doesn't make any sense to look at prime factors that are greater than half the number. Okay, it really doesn't make any sense to look at prime factors that are greater than half of the number. All right, it doesn't make any sense to do that. So with that in mind, we can create the prime, the prime factors function. I'm going to call it prime facts. I'll just call it prime factors. Num. I'm going to create a local variable, module. Half of num is equal to the quotient. Okay, this is the integer division. Integer division, not rational division, but integer division. Quotient 7, 2 should be 3, right? But 7 divided by 2, is actually 3.5. Okay, so half of num is equal to quotient num2. I could even create another local variable, module. Possible prime factors would be cases, range 2 to half of num, n, we can do that, prime qn. And that's exactly what I did here. I'm factoring out my prime integers. Okay. And then prime factors helper, empty list, possible prime factors, num. What are the prime factors of 10? 2 and 5, because 2 times 5 is 10. What are the prime factors of 4,000? Let's see, 1, 2, 3, 4, 5. 2 times 2 times 2 times 2 times 2 times 5 times 5 times 5. What are the prime factors of 8,898? 2 times 3 times 1,483. Okay. So we can try it on this problem. However, well, I predict we may have an issue, and you're going to see what it is. All right. So don't confuse Mathematica with C, C++, or Java. Mathematica has a that's okay. Mathematica has a somewhat limited stack, not that different from Python, actually. Okay. What if so 10 factorial is this number. Prime factors, 10 factorial. This won't be pretty. Shift enter. It says recursion limits. Recursion limits. Okay, so even if I increase the recursion limit and iteration limits, and you can in Mathematica, there's still going to be a problem. You can increase the iteration limit and the recursion limit in Mathematica, but you're still not going to have enough memory to factor an integer like this. C could do it, C++ could do it, Java could do it, but Mathematica is a little weaker than C, C++, and Java. All right, so we have to be kind of clever about it. So first of all, okay, recursion limit. Yeah, 1024 stack frames. Iteration limit, 4096. So even if we were to increase this, recursion limit is equal to 1,000. I'm going to multiply by 10, 10,240. And then iteration limit is equal to 10,240, and iteration limit is, let's say, 40,960. You know what? It's still not going to be enough. It's still not going to be enough. Prime factors 10 factorial. Yeah, so we're still getting the same error message. So what I would do, what I would recommend is this. We need to, okay, abort the evaluation. Abort the evaluation. Chach, it's okay. Abort the evaluation. So this is what we're going to do. 10 factorial. Notice the 2 zeros over here. We have 2 zeros. So we have 100 times this number. We have 100 times 36288. 36,288. So why don't we do this? Prime factors 100. Prime factors 36,288. And that was pretty easy. Now, why don't we just sort the whole thing? Let's sort it. So we have 2, 3, 5, and 7. 2, 3, 5, and 7. I'm going to put this in, which problem is this? Oops. Okay, hold on a second. So this is problem 65. Problem 65. Okay. Chat, you can jump up. Count problem 65. How many 2s? Count problem 65. How many 3s? Count problem 65. How many 5s? Count problem 65. How many how many 7s? So your answer is very simply 2 to the power 8 times 3 to the power 4 times 5 to the power 2 times 7. Okay? Let's see if that's true. 2 to the power 8 times 3, 2 to the power 8 times 3 to the power 4 times 5 to the power 2 times 7. And that is correct. That is the correct answer. Okay, guys, I think we're gonna keep this short today because I have kind of a sore throat, so I can't keep talking and talking. Hopefully this was a good video for you. You can do a lot of cool stuff with Mathematica, but Mathematica has limitations. It's not as fast as C or C++ or Java. So for certain things, that can be a little bit of an issue, right? And let me see here. 1 second. I just want to see. Yeah, everything here looks great. No problems. All right, guys. You have a great night, great day, great week, great weekend, and we will communicate in the near future, okay? Take care. Have a good night. Bye-bye.